Hello.
Hey, Alicia.
Hi. Sorry, I was connecting my audio.
Oh no, it's okay. It's okay. Yeah. You finished all the Mentor One material today for next week.
Yeah, that was the cutoff. So I mean, it was it was kind of unexpected to see. I think it was radical halogenation again. It
Mm.
was like one of the very first reactions that we kind of learned, and like there was like more of that idea of like a single electron being like moved
Oh, like
in a
radical
mechanism.
movement.
Yeah, so like I was kind of surprised to see that. I
Yeah.
didn't know we are gonna bring that back.
Uh,
So
right, like whenever you see radicals, then that's always a sign of anti-Markovnikov addition, where the nucleophile attaches to the left subside or left subside of the alkene, like
oh.
carbon, right? Um, that's when you saw uh when we have, let's say, this alkene right here, and you react it with HBr, and you react to some sort of peroxide like that. R is
Mm-hmm.
any random hydrocarbon chain. It could be any random group, right? But the most important thing here is that bond between the two oxygen atoms. When you see this right here, um, we're gonna do an anti-Markovnikov addition where we attach the bromine to the less subcarbon of the alkene, the anti-Markovnikov carbon of the alkene,
Mm.
right? Which is this carbon right here. So we're gonna attach bromine on that carbon right there, like that. Okay. And another thing to keep in mind about this reaction here is that if you try to become tricky with this reaction roar here only does anti-Markovnikov with HBr, um, HS, like you can see this as SH, um, like RSH. H2S or RSH. Right. When you see HCl HI with roar, then that would still do Markovnikov addition, right? So for example, if we have HCl roar, then that is still going to attach the chlorine to the Markovnikov position, to the more subside of the alkene, like that, right?
Mm, okay.
Uh-huh. Yeah. um let's see, were there any like specific reactions that you were stuck with the most on what you went over today? Like there was a lot of reactions, or did you like have any questions on the practice midterm here? Because I think you could do this now, right? Because like, have you learned about ozonolysis yet, that reaction?
Yeah, I think so. Yeah, that was like.
Hmm. Yeah, that was the cutting up the alkene in half reaction. So that's like my favorite alkene reaction, because um when you have any sort of alkene and you react it with two steps, first step O3, second step dimethyl sulfide, think of this reaction as the scissors reaction, where you're gonna have a pair of scissors, right? And you're gonna cut this double bond in half and put oxygens in the middle right there to get these final products right there, right? Just cut the double bond in half, put oxygens in the middle like that to get your final products like that, right? In this case, we got two different products, this aldehyde and this formaldehyde right here. It can become more tricky if it is more substituted. So for example, let's say we have this alkene right here, and I react it with ozonolysis reagents. First step O3, second step dimethyl sulfide. I'm gonna do the same thing. Cut this double bond in half, put oxygens in the middle like that to give me these two products here, one ketone and one aldehyde. Now, I'm gonna give you a problem to work on, and then I'm gonna move on to 8B, and then I'll check it at the end later. Right.
Okay.
So, say we have this. Yeah. Let's say we have this molecule here, and we react it with ozonolysis reagents. First step O3, second step dimethyl sulfide. And when you see multiple alkenes, you're gonna cut all of the alkenes in half and put oxygen in the middle. So you're gonna have multiple products here. Right. Okay. So let's do this actually. Okay, yeah. So this would be the alkene that I want you to react this with ozonolysis reagents here.
Okay. And also, is it okay if you scroll up real quick where you like have the scissors?
Yeah. Uh-huh.
Okay, got it. Thank you.
Yeah. Mm-hmm. Yeah. Okay. So let's move on to Chem 8B. Oh, I know Madison, I got your questions about the homework problems. So do you want to go over those problems right now?
Yeah, if we can. Or if anyone else has obviously other questions, I think anything can apply.
Yeah. Let's see. Let's do these, and then I think this would be related to the 8B material. So the first one is talking about dehydration of 2-methylcyclopentanol, giving several products, and they want you to draw the intermediate that leads to the product shown below. So the reactant molecule that gave you is this 2-methylcyclopentanol reacting with H2SO4 and heat, giving you this product here. Right, and they put CH3 here, CH3 here, and they put alkene right there. Right. So let's think about this mechanistically. When we have a strong acid, sulfuric acid right here, we have to look for the most basic part of the molecule here, which is this alcohol oxygen right there. That's going to get protonated by the strong acid H2SO4, kicking out the HSO4 minus conjugate base, and that would convert this bad leaving group OH into a good leaving group OH2 plus oxonium ion. Now we can think of this as an E1 type mechanism now, because once we have this good leaving group present, we can kick it off to form our carbocation intermediate, right? And whenever we form this carbocation intermediate right here, we always have to look out for any carbocation rearrangement steps that we could do, like either hydride shift or methyl shift. We see that this carbocation is secondary, this one to the top of it is tertiary, and to the bottom it's secondary. We see that we could do a hydride shift to convert this carbocation to the more stable carbocation position right here, but that would not lead to this product that they give you right here, right? Because let's say we do the hydride shift, draw that bond out explicitly with the hydrogen, shift that bond with the hydrogen over there to get the more stable carbocation right here, right? This is going to be our alpha carbon, and these will be our beta carbons right here, right? So based on that intermediate, our possible alkenes would either be that, this, or that, right? Which is not this at all. So this product here is actually like a minor product where the intermediate to get there is not the most stable carbocation intermediate, right? It's actually going to be the one that you drew in the product, which is this one right here, before the hydrate shift, right? So have you tried submitting that as the intermediate? Oh wait, actually, for you right here, you drew the carbocation on the most stable position, which is the tertiary position here, but that would not lead to this final product right here, right? That you drew the intermediate after the hydrate shift.
Oh, I see. Okay.
Right. Right, because once we have this carbocation right here, to get to this minor product that they gave you, we want to grab this beta hydrogen using HSO4 minus as a conjugate base. Grab that hydrogen. That bond between the hydrogen being grabbed and this carbon here is going to break and make a double bond over there to give you this minor product here. Right? That is not a major product because that skipped the hydride shift that forms a more stable carbocation, and that does not form the most stable alkene that we can possibly get.
I got it. Yeah, and
Yeah.
that's correct. That makes
Mhm.
so much more sense. Thank you.
Yeah. Nice. But that's kind of misleading though, because like if this was on like a Levian's exam for 8B, she would expect you to draw the major organic product, and like some people might think that this is the major one, or did it say, let me read the instructions. Gives several products. Draw the intermediate that leads to the production below. Yeah, so it does say it does make several products, but it does not say that this is a minor product in the instructions. So keep in mind that this is a minor product because that skips the hydride shift, and this does not make the most stable alkene possible.
Awesome. Got it. Thank you so much.
Yep. Okay, so the next part here, provide the structure of the major organic compound for the following reaction. So in the reactant here, we have this ether reacting with HI excess in heat. So when you have an ether reaction, you're gonna have to look at this chart right here where I'm gonna say that this is the R group, and it could be methyl, primary, secondary, tertiary, and what kind of reaction it's going to be, right? And Levens, did she give you a table of priority when you do ether reactions with HX? Like, secondary is probably the lowest priority, right?
I believe she did.
Yeah. Let's see. Should be like
Trying to see if I can find it too.
yeah. Yeah, so this is a 118A chart right here from Levens, which could be the same as her 8B class. But let's check here. Primary, hindered, secondary, tertiary. This one here would do SN2 reaction, and all of these here would do SN1 reaction, where DE1 is minor. And then the priority, tertiary will have the highest priority, and then methyl, and then primary unhindered, and then primary hindered, and then the lowest priority is secondary substrate. Right. Okay. Yeah, so this table here with the ranking list is going to be used for ether reactions with HX. Right. Ether reaction with HX, where X could be chlorine, bromine, or iodine. Okay, so let's think about this mechanistically. We have a strong acid, HX, in excess amount. When we think about what we are going to protonate, we're going to protonate that oxygen there of the ether. Right, so we're going to grab that H, kick out the iodine, leaving group, and get this intermediate here. Right, where this oxygen here that got protonated gained a bond to hydrogen, giving it a positive charge. Now, once we have this, then we look at the chart, right? This R group right here is going to be a secondary substrate, right? Because this carbon here is attached to two other carbons, 1, 2. Whereas this carbon right here is a methyl substrate, because that carbon is not attached to any other carbons. Then we look at the ranking list here to see which one has higher priority. Methyl versus secondary. Methyl wins. So we're going to use methyl as a substrate here. So this would be our substrate, making this whole thing in the green outline our good leaving group for the first reaction because we have excess amount. But using the first equivalent of HX, that's going to be our good leaving group right there. And this right here is going to be our substrate, right? And you're looking at the table right here. If we have a methyl substrate, we're going to do SN2 reaction. The reason why we won't do SN1 reaction is because we don't want to break off or kick off that leaving group automatically because that's going to form a very unstable carbocation intermediate, right? This is a methyl carbocation, which is extremely unstable. It has no substitution, no R groups attached to it, making it very unstable. So that's why we don't do SN1 there. We want to do SN2 where the nucleophile is the I minus that got kicked out earlier in the first step, right? This I minus here is going to attack that carbon and then kick out that leaving group right there to give me this alcohol plus CH3I, right? So this is the reaction after the first equivalent of HI. But we have excess amount, so we're gonna continue the process by protonating this alcohol with HI and doing a regular alcohol reaction with HX now, making that into good leaving group oxonium ion, kicking off that leaving group to form the carbocation intermediate, and the I minus comes in to attack that carbocation to give me this organic products here. So our major organic products would be that and CH3I, right? And you could also say water that left, but that's not organic, right? So try these two for now, and if it doesn't work, include all three with water as well for the homework.
Okay, perfect. Thank you so much. That makes a lot more sense now.
Yeah, of course. And also, be sure to make sure that this list is the same as her 8B list as well, because this is from Leuven's 118A material, like this chart with the ranking list.
Okay,
Yeah.
I'll have to look back on that and make sure it matches up.
Yeah. Okay. Does anyone else from Chem 8B have a question or problem they wanted to go over? Let's see. Hey Wiley, do you have any questions or problems we want to go over for 128?
Not really. Not really.
128B? Not really. Okay. Okay. Are you learning about what are you learning about now in that class? Ethers or
Yeah, ether synthesis, reactions to ethers, some thiols.
thiols? I see. Yeah,
Yeah.
like Williamson ether synthesis. Like this kind of reaction here that we did earlier. Where was it? Like this right here with the HX, like that.
You talked about like making symmetrical and then unsymmetrical ethers.
Mm-hmm.
Yeah.
Symmetrical and asymmetrical ethers with HX H2SO4. I see. Yeah. I see. See. Yeah.
Yeah, with a hydrogen halide.
Mm-hmm.
Or no, that's the cleavage.
With H2SO4.
Yeah.
Yeah, H2SO4.
And a heat.
Yeah, H2SO4 and heat to make the symmetrical and asymmetrical.
Yeah.
Ethers. Yeah, I see. Okay. Okay. Yeah. Okay. So let's go back to 118B. Mazna, I am going to explain your question number 8 right here,
Okay.
which is going to be this reactant, benzene, with this good leaving group, chlorine, reacting with NaOH, and water. So we see we have a good leaving group present, which is that chlorine. And we have a secondary substrate, right? Because this carbon here attached to the leaving group is attached to 2 other carbons. And our nucleophile base here is this OH minus, right? Which is a small, strong base, strong nucleophile. So all of these signs here, good leaving group, secondary substrate, and a small, strong base, strong nucleophile, is going to be E2 Zaitsev. We want to make the more stable alkene, right? So this is going to be the alpha carbon, the first carbon attached to the leaving group. These right here are going to be the beta carbons, and I'm going to draw out 1 beta hydrogen for all beta carbons. So that's the beta hydrogen for the left beta carbon, and I'm going to actually draw out all 3 beta hydrogens for this beta carbon here. One is going to be flat, one is going to be wedge, and one is going to be dashed. Right. So because we are looking for the Zaitsev E2 product, we want to look for the most substituted beta hydrogen, which is the one on the left right here, right? But we cannot grab that more substituted beta hydrogen right away to make a double bond here and kick out the leaving group, right? Because of something called the anti-periplanar transition state. Which means that this beta hydrogen here has to be anti or opposite to the leaving group. We see that this leaving group right here is a dash right now, and this beta hydrogen right here that we want to grab is also a dash. That's not good, right? Because they're not anti to each other. What we have to do is we have to rotate this single bond right here, right? I'm going to rotate that single bond right there, and I'm going to swap the methyl group and chlorine around, right? Like that. I'm going to keep everything on the left side stationary. So when I do that rotation, I'm going to have this resulting intermediate here. Right. This is the bond that I'm rotating right here. So that stays still. But now the methyl is down here. The chlorine is up here. But when I do that inversion, right? When I do that rotation, this dash chlorine here inverts into a wedge chlorine. Right. The reason why it inverts is because I want to say that this molecule is identical to this molecule here. If I were to assign R and S to this chiral center, let's practice that for stereochemistry. How would you assign R and S for this chiral center here? Here, the one that is attached to this chlorine.
Oh, well, like doing the priorities thing.
Yes. Mm-hmm. Let me draw it out here so it's neater, so then not a lot of things are in the way. Yeah, we want to assign priority. I mean, R and S for this chiral center right here, in red.
When it's wedged or when it's dashed?
When it's dashed. When this chlorine leaving group is dashed right now.
Oh, okay. Sorry, I'm writing it out.
Mm-hmm.
Be S.
S. So, let's see. 1, 2, 3. Looks R, but it's actually S. Yes, this is S, right? Because our lowest priority group here is on a wedge, not the backside, so we have to flip it to what it actually is, S, right? So because it's S, and if I rotate that single bond right there to give me this rotated molecule, I want this chiral center here to also be S, to say that they are identical, right? And to make it S, this would have to invert to a wedge, because this is going to be 1, 2, 3, going this way is counterclockwise, so that is S, and it stays S because the lowest priority group hydrogen is already on the backside, so it will stay as S. Right. I could not leave that as a dash hydrogen chlorine, because if I did that, then the chiral structure here would be R, and then they will not be identical molecules anymore. Right. I want to react this with the identical molecule after I rotate it, so that's why I'm gonna invert the chlorine's dash into a wedge like that. Right. After I do that rotation of the bond. And that's really important, because now if we look at this beta hydrogen that we're interested in to grab to make the more stable alkene, that beta hydrogen is now anti or opposite to the leaving group, right? It's the beta hydrogen is dash, the good leaving group is wedge. So then we could now do the whole mechanism. Grab that hydrogen, make a double bond there, kick out the leaving group to give us this alkene here. Right there, like that. Right. On the key that I gave you, I forgot to draw in that methyl group right there. That methyl group is this methyl group right here.
Okay.
Right.
Okay, I think I understand that. I think the rotation thing was just confusing me.
Yeah, the rotation of the bond.
Yeah.
But do you get the point of why we did that rotation of the bond though? Like why we had to do that for this problem?
Yeah.
That's good. Because if we did not do that and we just like went straight for the attack on this substituted beta hydrogen to make a double bond there and kick out the leaving group, we would end up with this alkene right here. Right, which is not correct. Right, this right here is a trans alkene, whereas the one that we had right here is a this right here is an E alkene. We can't say transfer cis because transfer cis is only used for exactly 2 substituents. Right, this alkene here has 3 substituents, so this alkene on top is E, this alkene on bottom is Z. The correct answer would be this Z alkene right here.
Right.
Yeah.
Okay. Thank you.
Yeah. Of course. Okay. What are you guys learning right now in Levin's 8B class? Oh yeah, I never asked. How was the first quiz? How did it go for you guys? The first 8B Levin's quiz, 20 minutes, right? I think. Was it fast paced?
I thought it was. It was only 20 minutes.
Yeah, I know.
I know, like some of my friends finished and they thought it was fine. So.
Dang. Was it the vocab section that you ran out of time on, or did you like
I personally started with that first and then cracked out the other stuff, but I'm not sure.
Right.
Side of that.
I see. Yeah. Did you like do it like from beginning to end, or did you like skip to the parts that you knew knew how to do first, so that like you get the most points as possible, and then like at the end do the ones that requires more thinking, requires more time?
That's exactly what I do, at least.
Yeah. That's good. That's good. So don't get stuck on one problem. Like if you get stuck and you think that a problem's gonna take you a while, skip it and come back to it later. You know, you have no time for that right at the beginning for Levens.
Yeah.
Okay. What are you guys learning right now in 8B? Let me check. Let's see.
I think we're still on alcohols and ethers. I think we're still really like wrapping up ethers. Like
ethers, yeah.
The different like types of reactions with like HX. That's what we did, I think, this last lecture. And reactions with like strong acids.
Strong acids, yeah. H2SO4, HX, alcohols, ethers, those things. Yeah.
I did send you, I think me and Talia had the same question we wanted to ask about one of our labs. I sent you a picture of it. It's like the last problem, number 4.
Oh, I see. Yeah.
Regarding it was regarding what we kind of talked about earlier with the equal and minor, like what do you call those?
Products, equal minor products. Yeah.
I think.
Yeah, colorful compounds absorb visible light. This absorption often due to excitation of a conjugate system. Green has a conjugated delocalized pi system. Draw its resonance structures. One structure is equivalent to the original structure in its contribution to the resonance hybrid. The other structure is more minor contributor to the overall hybrid. Okay. So there's two parts, part A and part B. Part A wants to draw out a resonance structure that is equivalent to the major resonance structure, which is this one that they give you here. Whoa. No. Yeah, there we go. Okay. Positive charge, and then benzene right here. Okay. And what you got here is you made a double bond right here, shifted this over, make a double bond there, shifted that over, make a double bond there, and boom. Like that. Yes. That is going to be the equivalent resonance structure, right? Where this nitrogen here has an invisible pair of electrons that you drew out. That's good. Which is going to move to make a double bond here, and then shift all these pi bonds over like that to give you the equal resonance structure here, right? That is correct. Erase all this. It's neutral. Double bond, positive charge, double bond, double bond, double bond. Like that, right? Yeah, so this right here would be an equal resonance contributor to this right here, right? Because we have a positive charge on the same atom, nitrogen, and every single atom here has the octet rule. That's good. For part B, they want you to draw out the minor resonance structure. So this is the major one that we're looking at. And then what you tried here for this part was shifted this here, boom, 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 boom. And that would give you your minor resonance structure. Yeah, you got that correct. But that positive charge right there that you erased on the minor contributor is supposed to be there still, right? Because that carbon lost the bond, so that carbon should have a positive charge, right? So these are all the arrows of that, of this minor resonance structure here, and I'm going to explain why here. Yeah. Boom, 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 boom. Right. Now this one might be tricky for some people because they think of a positive charge, and they think that that positive charge should be on the less electronegative atom, right? Which is shown here in this case, right? So some people would say that this right here is the major resonance structure, but it's actually not. This is the minor resonance contributor, because the most important rule or factor that determines the resonance contributor stability is the octet rule. Every single atom has to fulfill the octet rule, right? Every single atom here in the structure fulfills the octet rule. But if we look at this minor resonance contributor right here, that carbon does not fulfill the octet rule, right? Even though the positive charge is on a less electronegative atom, carbon, this carbon here does not fulfill the octet rule, so this is considered the minor resonance contributor right there.
So just to clarify, it's considered the minor because it doesn't completely fill the octet rule versus the other one where it does?
Yes.
Okay.
Yeah. Every atom here fulfills the octet rule. This one here does not fulfill the octet rule, minor.
Okay, got it.
Right.
Okay, that makes sense.
Yeah. And don't forget this positive charge here that you erased on the minor resonance structure.
Thank you.
Yeah. Okay. Let's see. Check. Good. The alkene reaction that Elisa tried. Let's see. This one. Yes. And to note. Okay. Share screen. Yes. Okay. Yes. Scissors reaction, ozonolysis. Cut the double bond in half, all of them. Put oxygens in the middle, giving you this product. Okay, yeah, so this one here is tricky because let's look at this here. Once we cut the double bonds in half, we put oxygens in the middle like this. Right, so this right here is good, that's correct. Right, that's one of the products, which comes from this right here. But this one right here, right, it's still attached to the ring. So
Oh yeah, it keeps everything else. And I think that's kind of what I did for the last one where I kept everything attached to itself. Like even the ring and everything. I think I just kind of missed that there.
Right, yeah, like everything else attached right here, like
Yeah.
that, like right here, right? Like you keep it attached, but I think you did it one at a time, like you did this one at a time, but all of this
Yeah.
is happening at the same time, simultaneously.
Right.
Yeah. Yeah, which would give you like these products here if you did everything at the same time. Wait, 3 different products. 1, 2, 3, like that. Let's get.
Oh, so you're saying you attached like that whole structure with carbonyls?
Yes, this whole structure here. Notice how we did not cut
Oh.
this at all with any
Oh,
others.
okay.
That stays right there, right? We just cut all of the double bonds in half that we cut, right? So that's the cut right there, that's the cut right there, and that's the cut right there, right? These bonds here are not cut, so they stay the same. They stay right there, right? Because if you get this right here, like that means that you cut this bond somehow, but we did not cut that bond out of the ring.
Right.
It's still right there. So these are our only 3 organic products here.
Okay, that makes sense. I think I didn't do enough practice to understand like this is their that's a whole structure altogether.
Yeah, that's good because like you could do it like this, right? But you know how it's kind of messy.
Yeah.
You could like redraw it into a more neat bond line form. Like if you count it like 1, 2, 3, 4, 5, 6, 7, 8, you could do like 2, 3, 4, 5, 6, 7, 8, and then you could number them like 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Where carbon 1 has the carbonyl aldehyde, 2 has the ketone, 3, 4 has this CH2 aldehyde, 6 has that ketone, 7 has that methyl, and then 8 has nothing. So this right here looks neater and easier to grade, but you will still get full credit if you draw it like this, right? So I would not draw it like this because that's gonna waste some time in the test, right?
Right.
UTA would be able to read what this is for ozonolysis.
Okay.
Yeah. Let's get. Yeah. Okay. So, Layla or Elysia, did you guys have any other questions about 119B that you guys wanted to go over? Or do you guys want to do more synthesis problems and bring everything together, all the reactions you learned so far together?
Maybe if we were to go over like a few other ones, like like I know there was like the alkenes dimerize and polymerize.
Oh, alkenes.
I think like those set of like different mechanisms kind of confuse me because I guess like understanding it and then applying it would be really hard.
Dimerize and polymerization. That's with alkene with acid, right? Yeah.
Yeah, like
Uh-huh.
ROR
ROOR.
or H2SO4. That one would be the cationic, and then there's like the radical version or like one.
Oh, right. Let me see here. Okay. So for that, wait. Before we go over that, let me give Madison an 8B practice problem to work on, so then I can check her answer after this right here. Let's get. This alcohol here reacted with HBr for that reaction. And for ethers, let's do this reaction with HI excess. Okay. Try these two reactions out, Madison, and I'll check your answer at the end. Draw the mechanism out and predict the product as well.
Okay, thank you.
So, isomerization, or was it polymerization of alkenes, Elysia? Polymerization?
Yes.
Yeah. Polymerization of alkenes. So I don't have his lecture slides up right now, like with this, but I'm gonna like try to explain it in the way that would make sense, and I will check the lecture slides to see like if this follows along with it, right?
Okay.
There's two ways. There's the one with H2SO4, and we're gonna work with that one first. Let's say we have this alkene right here, and we react it with H2SO4. What would you say the first step of the mechanism would be here if we have a strong acid reacting with this alkene?
That it protonates.
Protonates this alkene. And what would result after that protonation?
Then I say that in a formal carbocation.
Carbocation at the more stable position right there. And let's say it's that carbon right there. This carbocation right here is our electrophile, right? Because it has a positive charge. Let's say we have excess amount of alkene right here. Right? I'm going to bring in a second equivalent of alkene right there. And I'm going to attack this carbocation that is in dot right there with this nucleophilic carbon of alkene right there, the less subcarbon, right? The reason why I'm using the less subcarbon instead of the more subcarbon is because I want to form the more stable carbocation. Right. So this less subcarbon here is going to attack that carbocation and give me, like, this is the starred carbon, let's say. This is the new bond between the star and dot carbon. The dot carbon is attached to two methyl groups, so 1, 2. And this carbon right here on the other side of the alkene is now a carbocation. Like that. Right. So this one right here looks kind of weird. Actually, can I see like his lecture slides on this? But this is how I can say like we can extend or polymerize this alkene molecule by like just like using multiple versions of it and attacking itself to expand the chain like that. Right?
Yeah.
And then we could use another alkene to attack and then continue expanding the chain like that and polymerize like that.
Okay. I hope my slides did upload. I put them in the drive.
Yeah. Let me see. Oh yes, I got it. Yeah. It did upload. Yeah. Here. Okay. Yes. Carbenes. There's 3 carbene reactions. that makes the circular propane, dihydroxylation, ozonolysis, HBr, radical, dimerize, and polymerize. Oh yeah, so that is what we talked about, right? Because once we have this carbocation right here, what is one way that we can do to make an alkene here? Once we have this carbocation and we have HSO4 minus floating around, what would they do to form an alkene?
I'm assuming
think about like E1 type mechanism. Once we have the carbocation here and we look for any rearrangement steps, in this case, we don't have to do anything because this is a secondary carbocation. This is primary, this is secondary. It's already at its most stable position right now. So now we can look at the beta hydrogens here and here. Let's say this is HA, HB. Which hydrogen would you want to grab to make the more stable alkene here?
I say HB.
Yep, HB. So HSO4 minus here is going to grab that HB, make a double bond right there, and give us this alkene right here, which is the dimer. The dimer that we just formed, because we just did this like one time. We can polymerize and like bring in another equivalent of alkene and keep expanding it and get like a very big chain to expand the chain, right? Because if I do it one more time, like let's say this is the star, this is the dot, star attack the dot, we would get this right here, star, new bond between star and dot, dot is attached to a methyl group, and this whole R group right there, positive charge right there. And then we do the same E1 type mechanism at the end. We grab the most substituted beta hydrogen with the HSO4 minus, make a double bond there to give me this alkene right here, right? And now this is a trimer because we combined 3 alkenes together. This right here would be a dimer, this would be a trimer. Right? A polymer would be like many alkenes combined together like that.
Right. So, is this like the main the idea of those 2 steps is like one like it forms like a carbocation and then the like another of the the same same structure attacks the carbocation and then it forms that alkene and then it becomes stable, and then let's say like we add in another one, we form a carbocation again, and then we can add another one of its kind.
Yeah,
and,
we can do
it just
that.
branches out again.
Yeah, and it branches out again like this.
Okay.
Yeah. Right. And this won't show up in predicted product because like you don't know when to stop. Like if you have a lot of this, then you could have that. This will most likely show up in conceptual question or explanation type of question. Like this won't show up as predicted products, right?
So it's basically just like attacking itself until it creates a longer chain overall.
Yes,
Okay.
correct. It's going to attack itself to create a longer chain. Dimer if we combine 2 alkenes, trimer if we combine 3 alkenes, tetramer if we combine 4 alkenes, and then we can keep going on depending on how many equivalent or how many moles of this alkene we have. Right. If we have like if they specified like on the exam like 2 equivalent, then you know you're gonna stop here because we combine 2 alkenes together and we don't have any more alkenes, so we can't expand it any further. This is where we stop. Like if they specify how many equivalents we have, then it would be more clear to grade and where to stop this polymerization reaction.
Okay, thank you.
Yeah. Okay. So the other part of polymerization is radical. Do you guys remember initiation, propagation, termination back in medicine A, the very first reaction you guys learned? Right. The first part, which is initiation, right? That's gonna go from 0 radicals, and we're gonna break a bond open to form 2 radicals. So this is gonna happen with peroxide bond, ROR, ROOR, right? This bond here is extremely unstable. The single bond between two oxygen atoms, unstable, which makes it very reactive, right? So for initiation, I'm gonna draw out the ROR like this. If we put heat there, that energy is going to like homolytically cleave that bond where there's two electrons in this bond. One electron is gonna go onto this oxygen atom. The other electron of the bond is gonna go to the other oxygen atom. And I'm drawing single hook arrows here to show the movement of one electron. Right, and that's gonna give us two radicals here, two OR radicals. Right, where this oxygen here, it has that one radical right there. Okay, now we're gonna move on to propagation, where propagation is going to exchange one radical for another radical, propagating the radical chain. Right, so I'm gonna bring in one of my OR radicals like that, and let's say we have some random alkene like that right there. And I'm gonna focus on one of the bonds of the alkene, which represents two electrons. One electron of that bond is going to react with that OR radical right there. The other electron of this bond right here is going to move on the other side of the carbon of the alkene, right? Giving us this molecule here. This is the OR. That's the new bond between the oxygen and carbon right here, right? This, if I starred that carbon in pink right there, that's this pink carbon right here. If I dot that O down there, that's that dot O right there. This is the new bond between them from these two single hook arrows, right? This bond right here, the new bond with two electrons, are coming from this one electron in the radical and one electron of that bond right there. The other electron of that bond is now on this carbon right here, right? And then we can keep going, like depending on how many alkene equivalents we have, we can keep going by merging those radicals together to extend the polymer chain, right? So if I want to do this in purple now, let's say this is the purple star, this is the purple dot, this is the purple dot, new bond between the purple dot and purple star. And then this purple star here is attached to not a double bond anymore, but a single bond where a radical is right there. And then you could keep going. Like you could add more alkenes and extend the chain even further. Like that. Okay. But
Okay.
this was a simple example where it did not matter where we formed the radical, right? But he gave you another example where, let's say we had the OR radical and you had this sort of alkene right here. Right, now it does matter where your radical would go to. Where would you say the radicals can be more stable at? At this carbon here or at this carbon right here?
The middle one.
Yeah, the middle one. So if we want the radical right here, then that means that this carbon right here, the other one would have to bond with the OR like that. And give us this radical right there, like that. Right? And then if we have another equivalent of that, then that means that this carbon at the other end would have to bind with that radical, forming that bond and creating another radical there. This. Right? If I star this, dot that, that's this star, that's that dot, that's the new bond between them. That purple dot is attached to a single bond, radical, chlorine, like that. And you keep going on and on and on like that. Okay. Yeah, so this won't probably show up in predicted product. This is more for a conceptual multiple choice question or explanation problem, right? Where you could polymerize or expand a chain by either doing strong acid, H2SO4, or ROOR, right? The difference between them is the intermediate that they go through. If you use a strong acid, sulfuric acid, H2SO4, the intermediate is a carbocation, right? If you use ROOR, the intermediate would be a radical, right? But both cases, both scenarios would expand the chain, would polymerize the chain.
You said the radical would be what intermediate?
Radical would be radical intermediate.
Oh,
Radical intermediate. Yeah.
okay.
Radical intermediate. Yeah. Which is the 1 electron thing right there. Yeah. Oh, and I see you guys went over a lot of practice problems in class.
Like we went over 3 problems.
3 problems, yeah. See, that's good. Synthesis. Oh, he gave you guys a. Oh no, actually, I want you guys to practice and review the reactions first before we actually do synthesis problems, because to do these synthesis problems, you guys have to be like very familiar with all the reactions, what product they give, and like the regioselectivity and stereoselectivity. Right, so we'll do more synthesis problems in other avatars, but for now I want you guys to like be familiar with the new reactions you guys just learned, you know.
Yeah, thank you. Is there any like challenging problems or something that you give for us for homework?
Yeah, let me give you some problems here for homework. Let's do let me give you this right here. Okay, let's say we have. Okay, let's do one. So this is gonna be after the oxygen mercuration demercuration reactions. I'm gonna give you homework on these other reactions, and then tomorrow I'll check them, and then we'll do synthesis problems related to these here. To all the alkene reactions. And okay, that's one. Another one. It's gonna be hydrants like this. Okay. Yes. Okay. First step, Br2H2O. Second step, it's gonna be some strong base. Let's say turbutoxide. Strong base. Okay. Yep. Next one is gonna be say that one. Gonna be yes, and be sure to draw out the stereochemistry if possible, if there's chiral centers, right? Because this is gonna test the stereoselectivity if the reaction is anti-addition or syn addition. Right? Yeah, and based off that, let's do. Let's see, how many more? 1, 2, 2 more, 2 more. 3 more, 3 more, yeah, 3 more. Okay, let's do this. Okay. Yeah, so this one we kind of did at the beginning, but just for extra practice, let's do this. Yeah, 1, 2, 3. Yeah. Okay. 2 more here. Oh. Wait, let me check what he did. No, he didn't really mention about the other part. So yeah, let's just do these 2 over here. Like this. Okay, and this right here, we would test the stoichiometry for sure. Let's do. That. You react this with. HBR or HBR with roar and heat. Okay. Elysia and Layla, I want you guys to do these 6 problems for homework, which are the reactions after hydroburst and oxidation, and then we'll do synthesis problems after we check these tomorrow.
Okay, and the last bottom one, what is it? HBRN was the other part of it?
Roar, ROOR, and heat.
Oh, okay.
Thank you. Where should we submit them when we do them?
Yeah, you could submit them through school message on the school website. Like you could DM me or Instagram or Discord or email. Like any way would work.
Perfect. Thank you so much.
Yeah, of course.
Thank you so much, Brian.
Yeah, of course, of course. And just for extra practice, do the ones that he showed you the mechanism for, just for extra practice, right? Just to practice that mechanism part of the exam.
Wait, what was it to show the mechanism?
Yeah, if he did show you the mechanism for the reaction, draw out the mechanism of the reaction as well, just for extra practice.
Okay.
Yeah. Okay. Because that's gonna help you determine the regional selectivity and stereoselectivity of the reaction. Like if it's anti-Stein addition or Markov-Markov versus anti-Markov-Markov addition. Like that mechanism is the foundation of those properties of the reaction. You could say like that. Right.
Okay, and then you were saying like for the ones that require like the dasher wedge, make sure to include those.
Yeah. Make sure to include those dasher wedge, and that's when you have chiral centers being formed. If there's no chiral center, you don't have to put wedge or dash. It's optional.
Okay.
Yeah.
Okay. Thank you.
Yeah.
Have a good night.
Thank you.
Yeah. Have a good night, guys. Yeah. See you guys tomorrow.
Good night.
Good night. Okay. Madison, were you able to finish these 2 problems here?
The second one, I'm like kind of confused on. The first one, I think I got. I'm not sure if I did the step correct, but so the OH group grabs the hydrogen, if I'm correct.
Right.
And then the hydrogen grabs like the Br.
The bond between the hydrogen and Br, right? That bond right there, right?
Yeah.
Those 2 electrons break off and goes to the bromine.
it
Right.
breaks to the bromine.
Yes. Yeah, those
And
two electrons will go to the bromine. Right.
doesn't that attack that carbon that the OH group is attached to?
Not yet, because once this OH gets protonated, right, it grabs the H. It now has a positive charge like that.
Okay.
Right. And are you saying that this Br minus here attacks that carbon and it kicks out the leaving group like that?
Yeah.
Yeah. So that's SN2 reaction. We won't think of this as SN2 reaction. Think of this as SN1 type of reaction, right? Because once we have our good leaving group present right here, do you remember the very first step of SN1 reaction? Like something will happen to this leaving group first, right?
Doesn't it like a carbocation
Yep.
forms, and then you have to like look at for the, is it not the intermediate, but the like it can move around?
Yep. Shift. Yeah. Rearrangement. In this case, we see this as a secondary carbocation, and we see that we could do a hydrogen shift to the left to make it more stable, more substituted, like that, right? And then once we have the more substituted tertiary carbocation here, that's when the Br minus comes in to attack that carbocation right there.
Once it's stable.
Yes, once it's at its most stable position.
Okay.
Yeah. And this carbon here, you notice how it's flat, sp2 planar, trigonal planar? The Br here could attack on the top side or bottom side. So we're actually gonna get two products here. One that is a wedge bromine, forcing that ethyl to become a dash ethyl, and one that is a dash bromine, forcing that ethyl to become a wedged ethyl. Like that, right? We get two different products here because the bromine could have attacked on the top side or bottom side, right? I could not say plus enantiomer here, right? If you drew out one of the products, I cannot do plus enantiomer, because enantiomers would be when all chiral centers changed, right? This chiral center here in, let's say, purple does change, but the chiral center in pink does not change. It stays the same. Nothing touches that pink carbon. So these are diastereomers of each other. Some chiral centers change, some chiral centers stay the same.
Okay, that totally makes sense. And then there are enantiomers whenever both chiral centers
change, right?
Correct.
Correct.
Okay.
When all chiral centers change, when all chiral centers change, like if there's 3 chiral centers, then all 3 would have to change to make them considered enantiomers.
And if only 2 did, they would be diastereomers?
Yes, right. If there are 3 chiral centers and only 2 changed but 1 stayed the same, then there would be diastereomers, right?
Okay.
Or if only 1 changed and 2 stay the same, then that would also be diastereomers.
Okay.
Yeah.
Okay.
Yeah. Okay. Now for this ether one with HX, this is probably the newer material with the ether reaction. With the table that I gave you earlier with the the chart, right?
Yes.
So what did you say the first step was here?
I said an SN1.
SN1? Yeah, right. Before we choose what kind of reaction based on the chart, what would the strong acid do to this ether though first? Right.
So what did I put? Doesn't it like cause it to break away or like break off?
Break off? Not yet, right? What we will do first is that this strong acid will protonate this oxygen here, right? Meaning that this oxygen here is going to grab the hydrogen and kick out the iodine like that. That's the very first thing we have to do, right? Once we do that, this oxygen here now has 3 bonds and a positive charge like that. Right. Now we look at the substrates attached to this oxygen. This one on the left is tertiary. The one on the right is primary hindered. Right. The one on the left is tertiary because it's attached to 3 other carbons. 1, 2, 3, like that. The one on the right is primary hindered because it's attached to 1 other carbon, but that 1 carbon that it's attached to has more than 1 branch. That's why it's primary hindered like that. Right. Now we are going to compare what has higher priority, tertiary versus primary hindered, based on the chart that I give you. Tertiary one, yes. So the tertiary one here is going to be our substrate, and if that's our substrate, this right here in green that I'm circling is going to be our good leaving group right there.
Oh, okay.
And like you said, looking at the chart, SN1 reaction is going to happen, right? Like if you look at the tertiary, it says SN1. Do you remember what the very first step for SN1 is, like we said earlier here? Once we have the good leaving group present, what's the very first step that happens?
You form your carbocation.
Yes, and we do that by kicking off the leaving group. Right? That bond right here holding the leaving group is just gonna kick off the leaving group to form the carbocation intermediate, which is this carbocation right there, having this alcohol right there. Right?
So then it's completely like separate.
It's completely separate now. This alcohol leaving group is now this alcohol, and this tertiary right here carbon that lost the bond is now positively charged, like that.
Oh, I see.
Right. Now, the I minus that got kicked out earlier is gonna come back around and attack that carbocation. Right. Before that though, we had to look for any carbocation rearrangement or shifts, but we didn't have to worry about that here because it's already at its most stable position. Right. We don't want to shift it anymore. Yeah. And that gives us this major product here. But that's not the only one, because we have excess amount of HI. And we have this alcohol here, so we're going to react this alcohol with a second equivalent of HI. This alcohol is going to get protonated, grab the H, kick out the iodine to give us
H2.
Yep, with the positive charge on that oxygen right there. And imagine if you kicked off that leaving group right here. So this is going to do another chart, right, which I haven't gone over, but I'll go over this with you tomorrow in office hours, or if you show up, or in our private session. But you know how this is a primary hindered substrate? We're going to do something very weird here. We're going to do a concerted hydride shift.
Concerted, like concerning.
Concerning, yes. This is very concerning. This is very rare and concerning. I did not expect this to happen, but this is gonna be good if it does show up on the quiz, right? So, the reason why we can do SN1 right away, like normal, is because when we kick that out, we're gonna form this carbocation right here, which is primary, and that's so unstable. We don't want that at all.
Right.
Yeah. So, because this is primary hindered, we're gonna do a concerted hydride shift where we see that next to it, we can form a stable tertiary carbocation, right? So I'm gonna draw out that hydrogen explicitly, and I'm gonna do the hydride shift and kick out the leaving group at the same time. Usually, you know how we form the carbocation by kicking off the leaving group first, and then once that carbocation is formed, we do the hydride shift. In this case, concerted or simultaneous hydride shift is when the hydride shift and the leaving group leaves at the same time, simultaneously.
I see. Okay.
Right. So that avoids forming the primary carbocation and skips straight into the more stable position right away.
Oh wow.
Right. Where we did not have to go through that primary unstable carbocation because of this concerted hydride shift.
Right. Okay.
Now that is rare. Like on her lecture slides, I saw she put like, or you put rare like that. Which is this concerted hydride shift right here with the primary hindered case.
Oh, that's what she was referring to.
Yeah, that's what she was referring to. And this could show up on the quiz if she decides to be tricky. Tricky.
Oh, okay.
Yes.
Oh, well, now I can keep an eye out for that stuff.
Yeah.
Okay, well, thank you so much. I know it's way over your time. But
yeah. And then, of course. Yeah, and these will be your final products, but iodine just attacks it and give you a final answer like that.
Oh, okay, perfect. Just those. It's both of those, correct? Those are your major products.
Both
or
of
is
these,
it a major and a minor?
No major and no minor. Both of these would be major because with excess, and there's no wedge or dash here because there's no chiral center here. If there was a chiral center here, then you put wedges and dashes.
Okay.
Right.
Okay.
And this one here would be changing. Like it could be a wedge or a dash because it's a flat carbon like that. It could attack on the top side, giving you a wedge product, or the bottom side, giving you a dash product.
Okay, got it. Awesome. Well, thank you so much.
Yeah, of course, Madison.
I hope you have a good night.
Yeah, you too. I'll see you in this weekend for our private session.
Yes, definitely. And I'll probably pop in maybe tomorrow, but definitely Thursday.
Yeah, I see. Yeah.
Awesome. Thank you. Have a good night.
You too, Madison.
Bye.
Bye.